So that's been his work. He came to us from Ohio University, not the Ohio University, as other universities in the state of Ohio, I believe. He can correct me if I'm wrong there, but I'll let him go ahead and get started.
Hey, you have that right, Kristen. Yeah, so I more or less went from one OU to the next on that end. But yeah, thank you everybody for coming today. I mean, to see 40 people on a webinar like this is a lot of people, which is awesome. So I really appreciate you guys taking that time to come and check this out today, all remotely. And I'll be talking to you today about the work that I've done, talking with the GLM, the ABI, and the things that we've been able to observe and we've seen from these sensors over the last year and a half, 2 years worth of work so far. So jumping right into that, I do have a few acknowledgements. I want to definitely give thanks to my advisors, Dr. Kristen Calhoun, Anthony Reinhardt, and Don McGorman, for their advisement, for their knowledge, and for their leadership and guidance along the way from this project. And I also want to thank my committee members, Dr. Cameron Homeyer and Michael Biggerstaff. Especially shout out to Cameron Homeyer for setting up the Zoom. That way we don't hit the 40-minute cap like all students currently have right now. And then lastly, for the support of not only my work, but also all the other graduate students' work and their studies. I also want to thank the School of Meteorology, SIMS, and NSSL. So for a lot of people, it might have been a while since you've last seen or done anything related to lightning or kind of the sense of that. So this is a little quick kind of lightning spin up. Of course, 2 slides just to kind of get us all back into the lightning kind of train of thought. So the primary mechanism that is believed to help induce charge within thunderstorms and eventually create lightning flashes is the non-inductive charge separation process. And that's shown here in the bottom left-hand corner. So this is caused by the interaction between ice particles and grapple particles in the presence of supercooled liquid water. And so this typically imparts a positive charge on those ice particles and then a negative charge on the grapple particles. Over time, these regions of charge separate based upon other kinematic and dynamic factors into different regions of a cloud or in a storm. So what you can get, this is what's called the traditional tripole. It's highly simplified. But what we can see is these different positive, negative, positive regions in a very traditionalized sense. And what we find is that the flashes tend to originate in these regions between here where the electric field between the two is maximized. So a flash will initiate here in this region and then propagate in through the positive and negative charged regions depending on where it starts from. And when observing that, we can see this with the positive, we can see different positive and negatively charged regions as well. But we can't see everything, as there are certain lower positive regions that maybe we can't see as well. So really the propagation of the flash is determined largely by the regions of charge from which it originates from. Now, of course, I said this is highly idealized. This can, of course, become much more complex. This is a study by Calhoun et al. 2014, looking at the infamous Geary supercell I believe from Telex. And what we can see is a very highly complex charge structure with lots of smaller regions of alternating flashes. And the Geary supercell had extremely high flash rates associated with it. And those regions of charge were definitely associated with that. And so really, lightning is, in a sense, not just a microphysical process. It's also related back to the thunderstorm kinematics and dynamics that all need to really be considered in order to help understand those processes. Now, as those lightning flashes propagate, we have to understand also how do we detect and measure these kinds of flashes, and that becomes important for the data that we see. What you've most commonly seen is from ground-based networks, which are measuring the electromagnetic radiation that is given off by each lightning flash. There are the national ground-based networks, such as the National Lightning Detection Network, or the NLDN. There's also the Earth Network's Total Lightning Network, or the ENTLN. The NLDN collects only cloud-to-ground flashes, while the well, the ENTLN does collect both in-cloud and cloud-to-ground flashes too. And those can be seen within national networks covering these large spatial domains. More localized but higher resolution sensors also do exist, and those are lightning mapping arrays, which are using these very high frequencies here that are all about on the order of 10 kilometers or so apart from each other. And what they're actually measuring is the individual breakdown as the flash is propagating. So you can get a three-dimensional view of the propagation of lightning flashes from the individual sources or points. So to show data for kind of comparing these two networks, we can look at the NLDN flashes, the ENTLN flashes, and the LMA flashes. This is all from 1 minute of data over the same time period and region. And so we can definitely tell differences in what these different networks see. But they all come in with data as singular points. And so really the question is, well, how representative is this data and how usable is this kind of data? We can tell there are a lot of flashes here, but how many, it's hard to tell on its own. We really don't have any idea how many flashes are here, just that there are a lot of them. But we can get different features from each network. Now, another type of sensor that maybe you might not have heard of, but has definitely gained lots of prominence over the years, are optical sensors. Those have their early development and testing about the late 70s to early 80s. Those popularities really didn't grow enough until about the mid-90s with the launch of the optical transient detector. That's the instrument here in the top center of the screen, which is about a 12-inch, 15-inch long instrument here on board that satellite. And so that ran for 2 years. After that, it was followed by the lightning imaging sensor, or LISS, that was on board the Tropical Rainfall Monitoring Mission. And so that flew for a number of years, and then now has been kind of almost replaced by a LISS that was installed onto the International Space Station. So we've been able to gather a fairly large global view of lightning production based upon these optical sensors, which is great. But in a real-time forecasting application, it's very hard to use this data because it's all from polar orbiting satellites, as seen here by the trajectories of each of the TRMM and ISS. So you might only have 90 seconds of data, and it might be another hour until you see that data, until the satellite passes over that point again to collect more data. So understanding the uses of this, that we really need a geostationary optical instrument in order to really utilize the optical sensors over these large spatial domains. And so enter stage right, the Geostationary Lightning Mapper, which is on board the entire GOES-R series of satellites. That's currently GOES 16 and 17, covering most of the Americas, the Western Atlantic, and the Eastern Pacific. So this is a space-based optical sensor with a 2 millisecond frame rate, about 500 frames per second. And so a resolution of about 8 kilometers directly beneath the satellite and about 14 near the edge. Now, the important thing about this is that the GLM is an event detector. So what the GLM is doing is it's measuring the background radiation that's emitted from the clouds and then looking for rapid changes in the brightnesses of those cloud tops. And those rapid changes are what the GLM is detecting on the individual pixel level as these singular events. It's capturing where those events are and their brightnesses. To help kind of give a physical kind of understanding of this, this is what the native GLM data would look like. And so what we can, this is provided by, I believe, by Lockheed Martin. This helps to show the GLM data kind of played out in this really great animation. And so we can see the cloud tops there and the lightning flashes associated with the flashes that are taken from the GLM. And so the GLM is operating both day and night across most of the North Americas and then also South America as well. We're covering a very vast spatial domains, all with a singular instrument. We can see convective features. We can see where leading lines of different fronts are. And so we can definitely get at these lightning in a much larger spatial context than what we have been able to before. But we have all these events, which is great, but then how do we get to flashes? So to get to flashes, all of those events are then fed into a lightning cluster filter algorithm, which takes those events that are all near or that are all adjacent to each other in a singular time frame, that 2 millisecond frame, and makes them into a group. those groups are then clustered spatially and temporally into flashes. Goodman et al. 2013 has a really great figure for that. So you can think of these individual dots as all those LMA sources from before, showing the propagation of the flash. But then these individual boxes here are the events. And those are what you would expect to see from Cloud Top that the GLM is picking up. The adjacent events are then put together into groups. So there's group 1 here, group 2 right here. And these groups are spatially and temporally close enough that they are able to be clustered together into a single flash. And the optical brightness of the flash is weighted then for the center point of that flash. The detection efficiency of the GLM was designed as above 70%, with the false alarm rate below 5%. Now, when looking at the output from the cluster filter algorithm, it's great that we can now gather flashes. But if you imagine the individual boxes as your individual events, the circles as your groups, and then the triangles as your flashes, we really we have lots of data that we can gather here. This is in 1 minute worth of data as well from a different case. But it's hard to understand spatially what this actually means. We know that there is lightning that happened here, and definitely more flashes are occurring in these regions here, but we still don't have a very good quantifiable estimate and overall flash characteristics of that data. And for that reason, that spawned the creation of what is called GLM tools. GLM tools was developed by Dr. Eric Running at Texas Tech. And what it does is it takes those relationships between the events, the groups, and the flashes, and it's able to rebuild the spatial footprint of the flash by using the individual events, because we know those flashes propagated through those regions. And that data is then remapped, or those flashes are then remapped to the ABI grids. And that's bolded because I'm going to come back to that later, and that's an important point. And those are in 1 minute composites. So we can get fairly high resolution spatially and temporally from the GLM, and we can be looking at GLM imagery instead of singular points in space and time. So some products that you can get from the GLM, this is some of them, the most kind of the key ones, but not all of them. There's flash extent density, or FED, which is a count of the number of flashes that are propagated through a single pixel over that 1 minute. So if you had 10 flashes that propagated through that individual 2-kilometer pixel over that minute, you would have an FED of 10 flashes. You then have the average or the minimum flash area. Those are both available. And that calculates the area of all the flashes that propagate through that pixel, and then it takes the average or the minimum value. There's the total optical energy, and that's taking the optical brightnesses that were observed from each flash and then accumulating those over 1 minute, or the event density, which is just an accumulation of all the events then over that 1 minute. So explaining it is one thing, but showing it is another. So we can show this now. This is the 1 minute of data from before with the NLDN, ENTLN, and LMA. And now we can compare that against the 1 minute worth of GLM data through GLM tools. And this is what that data looks like. So this is the flash extent density. So that area where we saw lots of flashes before, we see that as well with the higher FED value. So more flashes are propagating through this region. We also can see with average flash area that we have these large flashes out to the east, and we do see that also in the average flash area too. And then smaller areas down here with all of these smaller flashes. So we're able to provide spatial context for lightning data based upon the events, the groups, and the flashes all working together within GLM tools. Now, another feature that we want to talk about is the other Earth-facing instrument that is on the GOES-R series of satellites, which is the ABI, or the Advanced Baseline Imager. This has 16 spectral bands ranging from the visible to the near infrared to infrared wavelengths. And it updates across the continental United States. That's seen every 5 minutes. Now, with 16 bands, there are lots and lots and lots of derived products. And because that GLM imagery is on the same grid as many of these ABI products that are at 2 kilometers, it makes direct comparisons between the GLM imagery and these ABI Cloud Top products possible. So therefore, we can fully exploit both instruments on the GLM to help us understand, or on GO16, excuse me, for the cases of severe convection. So this has really helped us drive home our research question. So we came in with the overall idea of how can we increase the applicability of GLM data for both operations and research? And so from sub-questions we'll use to help us get there is, as single instruments that are in space, are there any geometric or spatial caveats to the ABI and GLM data? As we're looking at it, does a flash extent density value at one point, maybe in Miami, Florida, mean the same thing as the same number of flashes that occur in Rapid City, South Dakota? That's we need to find out. Also, what can we learn about gridded GLM imagery in thunderstorms when combined with ABI data? And how can we exploit this data to help us understand those storms in a more complete spatial and temporal context? So before doing any results, we have to, of course, build a data set. So we took two GLM products, the flash extent density and the minimum flash area, and we selected those for the study. We used the minimum flash area instead of the average flash area because, as was shown in the hazardous weather testbed, when you're comparing between the minimum flash area and the average flash area, very large flashes tend to wash out those smaller flashes, which can become more important. And I'll explain the importance of the smaller flashes later. But we want to be able to capture those smaller flashes. We also then we also took two ABI level 2 derived products, which were Cloud Top Height, which you can see here on the top right. This is at a resolution of 10 kilometers. And then we have the Cloud Top brightness temperature from the clean IR band. That's band number 13 over here. This is a slightly shorter wavelength than the legacy IR band you might have seen. And it does, the temperatures do come in a little bit hotter because there isn't as much water vapor that is absorbed by those bands. But it does give a much more clear defined image of convection with regard to that. We collected 7 weeks of data across the CONUS scene, and we coincided this time with the maximum amount of severe weather generally across the US when related to tornado, hail, and wind reports. Several severe outbreaks happened during this time, higher impact events. That's really what we're after with our study. Now, when taking the data sets and merging them together, we took the GLM gridded output and we matched it to the ABI temporally by creating 5-minute GLM composites of the data. We also then use a selective sampling method, which put all of the data onto the same resolution at 20 kilometers. We could have went with the 10, but we ended up going out to the 20 because of large, in order to incorporate any kind of rapid changes in the in the cloud top heights, as that lower resolution can at times hinder that data and the accuracy of those measurements. So by going out to 20 kilometers and then selecting the maximum and min value within each grid box, as we can see here, we're capturing those maximum values and then sampling from those areas and applying that to the grid cell. So we're just lowering the resolution, but we're making sure that we're selectively sampling the data that we want from those finer resolutions. So with all the data now matching a spatial and temporal grid, we can now get back to our research questions. But last but not least, we had to do one more section, which was some filtering. We had to filter out a feature that has been likened in the lightning community to the Bahama Bar, which is related to the GLM subarrays. And so those subarrays are the individual hardware components that are the sensors for the GLM. The crossover between those individual subarrays can create these higher flash values and flash values that aren't physically realistic, and also create lowered thresholds for designating a flash as well. So we created thresholds using the ABI and GLM data to, in a sense, filter out that data. So we took the cloud top temperatures that were greater than 270 Kelvin, flash heights that were less than 4 kilometers, and FED values that were greater than 2 flashes per minute. And the reason why we chose those values was because if we have flashes, or a thunderstorm that is producing flashes that are about 2 per minute, that means that we have a sustained updraft that is very well making it up into the mixed phase region with elevated cloud top heights. And so if you're seeing these kinds of things, we are essentially saying that those are not physically realistic. And overall, we actually did a pretty good job of filtering out these data points. Those figures aren't included, but if you want to ask about that afterwards, you can. So now hopping over to our first research question, which is, are there any geometric or spatial caveats? So if we want to think about the GO16 data spatially, well, let's look at it as a function of the viewing angle, how far you are from the sensor, and how that tends to impact the observations that both the GLM and the ABI see. So what you can do, if you do a spherical Earth approximation, do some geometry, what you can get is the viewing angle elevations from GO16 at these points. We then took the data and we binned them every 10 degrees from 20 degrees all the way to exceeding 70 degrees. So 70 to 80 degrees is also included. So we took all of these points from within the GO16 domain, and that's what we were really looking for. That's what we started to then divide up our data set with. So the first thing we want to look at when making our comparisons, we're going to start by looking at violin plots. Violin plots are a great way to show distributions of your data sets across multiple areas. And so what we see in the middle here, the dots in the middle represent the medians. This is the interquartile ranges. So it's a mixture of the box and whisker plots, and then also the density distribution. So we can get a really great compact sense of where our distributions lie. All of the green violins for each bin, these are representing all ABI cloud tops that did contain, or in our data set, that did contain GLM flashes, while the green violin plots represent the cloud tops that were randomly sampled that did not contain GLM data. So really we're comparing the flash locations versus the non-flash locations with respect to our cloud tops. So this is looking at cloud top heights in the first image here. And what we can see, first of all, is our median values for our flash locations tend to cluster around 12 to 12.5 kilometers in this region, with exception to those viewing angle elevations that are furthest away from the GLM, the 20 to 30 regions. We also notice that the upper percentiles as well don't hold up as well once we reach above about 40 degrees. The viewing angle elevations, as kind of the maximum values tend to decrease across there. So cloud tops aren't as high from those sampled regions. When comparing that against our non-flash locations, we can see differences between those distributions, that the cloud tops with the flashes are generally higher, but that becomes a harder distinction to make at these higher viewing angle elevation bins, as we can watch the median values as those rise to eventually almost become even with the cloud top heights. And so we can look at this and compare that also against the increasing bimodal distribution that we see in the data set, where we have these kind of clustering of lower values below 3 kilometers or so, and then the secondary kind of maximum of values that cluster above 8 kilometers, between 8 and 12 kilometers overall. And so really, what's driving this kind of distribution to our non-flash locations in the data set? And it turns out that this is actually more of a physical process than a geometric process. And so when considering our data spatially, we can look at our viewing angle elevation map again, and we can notice the continental versus oceanic coverage for each bin. We see, as we have the kind of almost the increasing viewing angle elevation, we have an increasing percentage of oceanic coverage. And so when comparing our 70 to 80 degree bin at the very bottom, which is almost entirely ocean, we actually compared that against Palm et al. 2005, which these are observations of cloud top heights in the Eastern Pacific. And they saw very similar distributions to that figure, where we had the low cumulus clouds that were being forced off of the boundary layer, and then also the upper level cirrus clouds as well. And so those are really helping to drive those distributions. So this is actually a physical process here, but it does mean that it is much harder just to take cloud top height on its own and say this region is producing flashes without considering other variables. Now the cloud top when looking at cloud top brightness temperatures, we can see median values here for all of our flash locations that are around 220 degrees Kelvin. Before I forget, also our y-axis is inverted. So colder cloud tops, which is our higher and more intense cloud top heights, are now in the positive y direction. And we then end up seeing, you can see differences in the medians between the flash and the non-flash values that are of considerable difference, especially so with these higher viewing angle elevations. It isn't as much so on these ends, but even if you took a line around 240 Kelvin and you drew that right across, that's a really great dividing line between the cloud tops that do have brightness temperatures that produce flashes at those colder cloud tops, and those that did not produce flashes against those. So this is creating these kind of subtle differences between the data sets, but definitely is a marked line that we can get from that. And what this means physically is that we have these updrafts that are helping to drive lightning production. They have to, getting above zero and getting into the mixed phase region just isn't enough. You have to be able to have sustained cloud top cooling and consistent glaciation in order to form these regions of charge to get these lightning flashes. So what have we learned so far? Kind of our quick check-in. We've showed that viewing angle elevation does have impacts related to the observations of the convection, especially so with the cloud top heights. And with brightness temperatures below 240 Kelvin, that they are very likely to contain lightning from the GLM. Now, going over to our second research question, what can we learn about the gridded GLM imagery and thunderstorms when combined with the ABI data? And we'll start with that by looking at all of our data in bulk. This can be a daunting figure at first, but what this is taking all of the cloud tops where there were cloud top heights and brightness temperatures, and also there were GLM flashes, and what we're plotting this as a 2D histogram of all the flash locations. This is over 4.6 million points that are in our data set, all being plotted on one figure. But what we're really trying to understand is when lightning is produced, what is the distribution of both the cloud top heights and the temperatures? So what we see in this 2D histogram on the x-axis, this is the cloud top temperature. The y-axis are the cloud top heights. So we would expect to see our coldest and highest cloud top heights as our most intense convection in that case. Now what we end up seeing right away is we see this inverse relationship that builds up this central axis where we have with decreasing cloud top temperature, we have increasing cloud top height, which is as we would expect to see, and that's a good sign. We also see a maximum here in the values that's right around below 12 kilometers or so, and then just below about 220 Kelvin within that range. But most of our points then fall above about 10 kilometers and below about 230 Kelvin in this case. So we are fitting up to this upper kind of point of our overall distribution. Now it's great that we can see where all of our flashes are in this height and temperature field, but we really don't get an understanding of how the changing features with height and temperature also impact the GLM variables, the flash extent density and the minimum flash area. Now, of course, it'd be impossible to plot all 4.6 million points on one graph. So what we ended up doing was we did a three-dimensional scatter plot where we randomly sampled 1,000 points in our data set and then plotted those again by their cloud top temperature and height. But this time, the size of the dots here are representative of the GLM data. So what we're actually looking at, this is the larger flash extent densities, higher flash frequencies are associated with the larger dots in this case. And we generally see a larger clustering of the dots here at the uppermost cloud top heights and temperatures, and then much smaller dots here at the bottom of the overall distribution. There are random outliers, of course. We are looking at we are scattering across a very large sample size, so flashes of all shapes and size and kinds can be included in this. But even when running this random sampling method over multiple cases, this is the distribution you end up seeing from that. So we notice the flash extent density, how it clusters here at the top. But if we change this now and look at the minimum flash area, you'll notice that all the largest flash extent density circles now become very small. we can go back once just to kind of show that again. So as we have those highest FED values that are up at these highest and coldest cloud tops, that we actually are then seeing our smallest minimum flash areas. And we see larger than minimum flash areas down here towards the bottom of our distribution at warmer and slightly lower cloud top heights. So it's interesting that we've now observed this inverse relationship between the minimum flash area and the flash extent density. But how well does this hold up? So now for the next section, what we're going to, or the next graph we're going to end up showing is taking the minimum, we're going to be looking at the minimum flash area plotted again as the size of the pixels, but only now we'll be looking at that in context of the flash extent density. So we'll be looking for cases of high flash rates. So all of these points are sampled with FED values that exceeded the 90th percentile. So we really wanted to get at the highest flash rates, the most intense convection, and really understand what the minimum flash areas look like. And as we can tell from the before and after, it's a very day and night difference here, where we now, with the highest flash rates, we can absolutely see these smaller, or these much smaller minimum flash areas as compared to before. We also do see an upward shift in our data, so the higher FED values are associated with these higher and colder cloud tops. So it's great that we can see this relationship, but the question that I kind of posed earlier, and then I'm going to come back to now, is why should we even care about flash rate versus area? What is this actually telling us? So as was mentioned before, the propagation of flashes is largely determined by the regions of charge from which they propagate through. So that can have big impacts on the convective versus stratiform regions and what those flashes take on with their physical characteristics. So this Brunning and McGorman 2013 figure is a great example of these kind of different setups that you can get. So we're actually going to start with panel B here at the bottom. You can imagine that this is the kind of structure you might see very close to a very intense updraft, where you have lots of charge separation that's readily occurring. You have lots of turbulence that's also occurring around the updraft, that's creating these smaller pockets and these turbulent eddies as well, and these smaller pockets of these charged regions, excuse me. And this creates lots of interaction between each individual section. And therefore you can have lots of flashes, but the flashes are very confined to these smaller charge regions. So you can get high flash rates with small flash areas. Conversely, maybe you're out in the stratiform precipitation region of a QLCS, and you'll see these larger stratified regions of charge. You can get these huge amounts of charge that build up in these layers. But because they are interacting over such large distances, you might have a single flash that occurs that then propagates in these large outward horizontally expansive regions of the storm. So we see then in this case, very few flashes, but flashes that have extremely large areas. This can also be related back to the convective evolution. As you would see a strengthening updraft, you're then also increasing the turbulence within the storm and also your rates of charging. And then therefore you would also see increasing FED and lower MFA if looking at that from a GLM perspective. Now, how can we verify this? And also, does this change for severe storms? Are we able to see this kind of feature in the convection that forecasters would be most concerned with within the warning decision process? So we're going to rely on an old friend, local storm reports. And yes, there are many caveats of using local storm reports, one being that there is inherent clustering of reports near cities. As you can see, this is the 7 weeks of LSRs that we're going to be collecting from tornado, hail, and wind reports. And there is a large clustering at large cities as well. We also then see that the number of wind reports and hail reports isn't always representative of the intensity of the event. And not every single severe event is captured in this data set. But what we're really trying to get at in this case is where these severe phenomena are occurring and what the GLM and the ABI are seeing with respect to that phenomena. So what we did was we took that data set that we originally had, and we created an LSR flag for all of the points that were available. And we plotted each LSR point and then found the nearest 9 points on that 20-kilometer grid. And those were then sampled to create about a 30-kilometer buffer around that region. And that was done mostly, one, because of location errors in order to capture spatially what was going on, but also we wanted to mitigate what's called parallax correction between the observations that occur at cloud top and the observations that occur at the surface with the LSRs, as those two are not going to be happening at the same place. We then also, for any kind of temporal errors, we tried to use a 10-minute window around each LSR to help us capture that. We tried several different windows, even up to 30 minutes prior to the LSR, an hour around it, and there really wasn't any difference in our distributions, but 10 gave us some fairly clean results. So if we go back to that same 2D histogram from before, we can already see some differences, along with the reduced sample size, of course, but what we can see is the maxima has shifted considerably up to around 205, 200 Kelvin, and then right around 14 kilometers with that center. So we've had a large upward shift in our data. We've also can again see the height and temperature relationship, and that is actually even more strongly defined in this case. So we are sampling now a much more intense region of convection than what we were before. And so this really now begs the question of how do our GLM variables change when moving around in this space instead? And so what we see that when plotting the FED variables as the flash, or as the size of each scattered plot point, we see very high values here that occur at the ends. The core, of course, is very obscure, but one reason that it is so obscure is because these individual dots are larger now than as compared to before. And they are, again, of course, shifted up and to the left. When looking at the minimum flash areas, lots of the flashes become very small. So we again are sampling a higher distribution in the FED values. And we're now seeing that inverse relationship between the flash extent density and the minimum flash area. So we've now learned that those flash characteristics that are related to thunderstorm morphology and the intensity of thunderstorms can also be observed by a merged ABI and GLM dataset. Now the last section we're going to cover here is, well, it's great to have this bulk study to look at all this data and see these kind of broad relationships, but how good are those in reality at the storm level? With individual thunderstorms, do we see these relationships? So we're going to be wrapping up here on a case study. This is from May 24th of 2019. Well, we're going to be following a supercell from CI all the way up to its upward or upscale growth into a QLCS containing all three hazards along the way. And there also were other storms in the area due to a weak cap. And so this created the question of which storm should the forecaster be focusing on when looking at the likelihood of issuing a warning for one. Looking at the setup for that day, just as a quick little kind of setup, we have a stalling cold front that was spread out across central Kansas and then into the Oklahoma and Texas panhandles as well. And with no cap, there was convection that was already starting earlier on in the day, and it was a fairly messy scenario with that regard. But we do still see these nice southerly winds that are backing in here with these elevated dew points up over 70 that are going to be pushing into southeast Kansas, creating a really nice environment for storms on that day. Deep layer shear was also very strong on that day and was supportive of supercells. So we're going to skip ahead to initiation of the storm that we're going to be observing today. And this is going to be happening at 20 UTC. This is observed by the MRMS reflectivity at lowest altitude, or the Rala product. And we can see reflectivity values that exceed easily 35 dBc. So we definitely have ongoing convection that has fired up right here at the very southern end of Kansas here in Sumner County. When looking at that in the GLM data, FED values are fairly low in that region. Not really a lot of activity as of yet, likely from other flashes in the area. Again, minimum flash area, we're not really seeing much. It's a kind of a scattered distribution of what the sizes are, not very organized. We're seeing flashes as low below 2,000 and well above 4,000 as well in this area. The same story can be said with the ABI data. You can see the initial initiation here from the brightness temperatures. And so reaching below that 240 Kelvin region, so this is a likely region to begin to form or begin to have lightning flashes associated with it. The cloud top heights, though, on the other hand, the resolution actually turns out to be a little bit too coarse for right now, and we really aren't able to see that initiation because of the storm to the north that is impacting those observations. Skipping 40 minutes ahead, as the storm began to grow and intensify, we now see a larger region that exceeds about 50 dBz from the MRMS Rala product. That increase in intensity is also noted in the GLM. This is actually the central part of that storm there at the base of the updraft. And we do see these higher FAD values that exceed about 60 throughout large portion of this region here. So we also then inversely see smaller minimum flash areas that are well below 2,000 square kilometers, even below 1,000 kilometers in several areas within this region. So this storm is beginning to pick up in intensity. From the ABI, we see, again, a very similar story, decreasing temperatures here, and then largely increasing cloud top heights, with cloud top heights now knocking on the door of just below 16 kilometers in height. Now, if we go 20 minutes later, this is the initial development of what we observed as the supercell. And we began to see supercellular features that formed within that storm with a defined hook echo, and also a rightward propagation of the storm from the main storm motion, slightly off to the east as compared to the other ones pushing directly northeast. And so we have the supercell that is readily intensifying, even a region now that's over 55 dBz from the Rala product. And that is again reflected in the FED and the MFA values. Very high of a maximum here that is well over 90 flashes per 5 minutes. We also then have minimum flash areas that are below 1 kilometer and are below, 1,000 square kilometers. And when comparing these storms with the other ones in the area, this storm is showing the greatest intensity at the time and the highest likelihood of producing severe weather. Now, if we map out that over the next hour, we actually watch that supercell go on, and it produces several hail, tornado, and wind reports associated with it as it continues to move off to the east-northeast, kind of northeast movement. The flash extent density values remain fairly high, while the minimum flash areas also remain fairly low in that regard. Near the end of the loop, you begin to see the storm lose some intensity as well as the FED drops off, and there's a slight increase in the minimum flash area. This can then be seen when played out from 22Z out to 0Z to May 25th. As that storm eventually dies off, we actually see this upscale growth of the storm and organization with other storms in the area to create the early resemblings of the QLCS that eventually pushed eastward into western Missouri. And so we're able to see then from a QLCS perspective, these higher FED values along the leading convective edge, smaller values as well, and then the inverse, where we have lower FED values and higher MFA values in the stratiform region. So we've been able to then use both the ABI and GLM products here in this case to help us understand storm evolution and its overall movement, as well as creating characteristics that are related to the intensity. So they can be readily applied to these individual thunderstorms. Now, from here, where would we like to go? I mean, it'd be great to eventually take these observations and use what's now available, which is parallax-corrected GLM imagery, also in GLM tools, and then making comparisons of the GLM data with ground-based observations like radar and other networks. This work also, because of what the variables involved, largely supports what's called a GLM infrared RGB product. And this RGB product is currently undergoing testing, the idea behind it is by taking the inverse flash rate and area, and also the decreasing brightness temperatures from cloud top, is that you're able to actually capture those in a singular product that forecasters can use to help them understand where the most intense convection is and where more stratified flashes are, or where more stratified and larger flashes are occurring out in these regions. So this really does help support that study, or the study of this, and hopefully with future development of the RGB product into forecasters in operations. Also, just as we are wrapping up here, some sources of the GLM data, just so that way those are out there. NOAA class has GLM data. Also, the GO16 data archive, which is run through the University of Oklahoma. There's also Google Cloud and Amazon Web Services through NOAA also have that data there as well. So there's a number of places that you can get this data. If you would like to get the gridded GLM imagery that you saw today, along with downloading that data, you would also need to use GLM tools, which is available through GitHub. Has really good documentation with that, and is fairly easy compared to a lot of developer code to set up and run. So lastly, here's my sources, and I'll leave up the conclusions. If you would like to talk or email me at all, or if you like afterwards, but also I'll take time as well for questions if anybody has any. So thank you guys so much for tuning in, and if you have any questions, feel free to fire away. Any questions?